We're going to look at two features of the algorithm, tie-breaking and load balancing. So until so far we assumed that there are no ties, meaning weights that are equal, so that we cannot set a preference. But now we're going to allow this because in practice ties happen. Ties are only a problem really if edges have the same weight that share a vertex. In that case, we need to decide who is the preference, and that's tie-breaking. Here is a situation where we have ties. Three edges all have weight 10, and we have a triangle where x can propose to y, y can propose or set a preference to z, and z to x. And we have three preferences set, but no mutual preference and no matching happens. That's a preference cycle of length 3. A solution could be to use another weight to set a preference to break the tie, a secondary weight. And that could be, for example, if we number the vertices and each vertex is equal to their index, then we could set a secondary weight omega 2 of uv to be equal to u plus v. And then if we want to compare, we only need to compare edges that are incident to the same vertex, in this case v. So if u, v, and u prime v are edges, and we compare them, we want to see whether the first one is larger than the second one, then we compare u plus v to u prime plus v, or just u to u prime, meaning that if you have a higher index, you win. And that's a way of breaking ties. Now, is having ties a feature or a bug? Is it good for us or is it bad for us? Is it undesired behavior? Or maybe we could see it as an opportunity because there's more choice. In the sequential case, we can use it by taking as the preference one of your suitors. If among the ties there is someone who already prefers you, then you set a mutual preference. And if there is no suitor among the ties, then you do it randomly. And that could work, will work in the sequential case, but not in the parallel case. Question to you, why not? Well, in the parallel case, things happen simultaneously. So there is no such thing as you arrive first. There's no total order in setting the preferences. And also the information is distributed. So that's why it will not work in the parallel case. Here you see an example. We have a blue processor, a yellow processor, and a black processor. And you see the partitioning. Here we have again the ties, where x proposes to y, meaning sending a message. Y proposes to z, z proposes to x. It can all happen in the same superstep. And then suitors are being set. For example, the suitor of y is x, and so on. But still, no matches are made. And x, y, and z will never set another preference. So they will not be matched. That's a problem. A solution to this is to prefer the girl or boy next door, enhancing locality. What you could say is, let's define a weight, omega 1, of uv, which is 1 if phi u equals phi v, meaning they're on the same processor, and 0 otherwise. And this enhances locality because there's a local preference, and thus reduces the communication, and that's a good thing. Furthermore, whether you have a mutual preference can be checked locally, immediately. There's no communication needed for that. So it also speeds up the algorithm. The quality of doing this, so first breaking ties by the secondary criterion locality, and only then by the index, the quality is the same as just taking the index, because in principle all ties are equally good if we don't know anything more than that. A problem with this approach is that you get non-determinism, because if you have different numbers of processors, you get a different solution because of the ties. A good thing is that the guarantee of having at least half the optimal weight still holds. That was ties. Now about load balance. We can use a partitioner to get a good balance of the vertices, or even of the vertices and the edges, for example using the Mondrian partitioner, but still the algorithm can be unbalanced. And why is that? It could be that in the first superstep the processor 0 has a lot more work to do, and then in the second superstep processors 1 and 2, like in this picture, have a lot more work. And that is that's a pity, because then most of the time some processors are waiting. So what can we do? Well, the observation is we need not wait for the work queue to be depleted until we synchronize. What we could do is synchronize earlier, because synchronizations mean communication, mean messages are being sent, and messages cause new work. They generate new settings of preferences. So what you can do is you count how many operations you have done. Or if you don't want to count every single operation, you can use the sizes of the range. If you have, for example, length of adjacency lists, you can use them to get a measure of how much work a processor has performed. And then once you get to W max amount of work, you stop and you call the synchronization. Or if you have no more work to do, of course, you also call for a synchronization. And then, since all processors more or less do that at the same time, in case they do have still work, then they synchronize more or less at the same time, and then everybody can continue the work. And this is what you get then. So by inserting synchronizations, you carry out useful work most of the time. But don't get carried away. Don't synchronize too much, because then synchronization time will be the dominant factor. How often should you synchronize? Well, we have a cost model to help us in this. For example, if L is the synchronization time, so synchronizing costs L, and you don't want to spend more than 20% of the time on synchronization, you could decide to take W max to be 4L. Then the cost of a superstep is 4L plus 5L plus L equals 5L. And only L of that is synchronization. The rest is useful computation. So that is a way of doing it. You could also use a timer, for example, if you have a timer and there are some fluctuations in the speed of processors, then you could do that. Another possibility is, if you want to prevent too much synchronization and you know that everybody still has a lot of work to do, you can take the work queues, the length of the work queues of all the processors, take the minimum of that, and maybe you need to normalize for certain speed in handling the work queues. And then you set W max to be larger than or equal to that, or equal to this value. And then you get a good, you prevent a lot of synchronizations that don't help anyway. Okay, so what is the communication cost of the algorithm? we know that if we send a proposal, we do get an answer, a reject or an accept. So along an edge, we have a message back and forth. It could also happen that two processes propose to each other for a certain edge at the same time in the same superstep. And then we have seen that you do not need to answer because both know that there is a match and they both know it's like accepting without saying so. And also in that case, we have two messages across the edge. So altogether, if we count how many edges are cut, and that's called the edge cut of phi of the partitioning. So it's the number of edges uv for which phi u is not equal to phi v. Then 2 times this edge cut is an upper bound on the communication volume happening during the whole algorithm. Think like a vertex is a philosophy of designing algorithms. If you have a good partitioning, for example, in our case, then the edge cut will be small and you don't have much communication during the algorithm. Most preferences will be local. For a bad partitioning, almost every edge is cut. For example, if you do just a random partitioning, this is what most likely will happen. So systems that are based on the BSP model, like Google's system Pregel and the Apache Giraffe, their motto is think like a vertex. A vertex receives messages, does something, and then sends messages. And that really means that we have our system with P, the number of virtual processors, equals N. So this is done for fault tolerance. So they are very fault tolerant systems. But if you think like a vertex, you also talk like a vertex. There's plenty of communication. Let's summarize. So ties in the algorithm can best be broken by preferring local matches and then set preferences for any ties that have not been broken yet by the highest index. Synchronize more often. That can help in balancing the load, but not too often. We have defined the edge cut as the number of edges for uv for which phi u is not equal to phi v. And using this metric, we can have an upper bound on the number of proposals, rejects, and accepts messages being sent in the algorithm of 2 times the edge cut. Final question. This is the graph we've already seen a number of times, 5 by 5 grid with weights in a certain fashion. And now we have bipartitioned it into a red and a blue processor. First of all, what is the edge cut of this graph, of this partitioning? It's an easy one. Now, a more difficult question is, how many supersteps will the algorithm, the parallel algorithm, perform for this graph? And you can assume then that we do not overly synchronize. We let each processor run until its queue is empty. And then another question, what is the total communication volume for this one?